After I got it dialed in well enough, it was time to see if the liquid-cooled scoop could handle a long ride in hot weather. Some of you probably already know that this meant I was going to the beach. I'm about 70 miles away from the beach, and it's one of my favorite spots to ride. It also means riding on long open stretches, through towns, and in traffic with lots of red lights, so it's good for stress testing. I left at about 11:30 a.m. on a sunny day that would reach close to 100 degrees. Add in high humidity, and if nothing else, the long day would stress test me. For the whole trip down, coolant temperature stayed between 130 and 160 Fahrenheit. It ran on the cool end of that in towns and slow cruising. Riding with more throttle was responsible for higher temperatures, but I never held it wide open for more than about 3 miles at a time. I had no complaints with those temps on such a hot day, but I thought the stop-and-go traffic of the beach may be the real test. I rode around for 3 hours with nothing more than breaks for gas or changing batteries in the camera, and I only had 2 complaints, neither of which were related to liquid cooling. The first was my center stand started scraping hard on turns. I later found that the clip holding its pin in place came off, so that was an easy fix. My other complaint was that I couldn't find any scooters to play with. I think it was just too hot for most people to want to do much riding. I did encounter a woman on a Kawasaki Ninja 250 that swerved in and out of the bike and bus lane to get around traffic. She made the mistake of sitting in the lane with me at a red light. By the way, I do realize I'm a fat guy on a scooter and I can't really keep up with most cars or bikes in a drag race, but that never stops me from trying. Most of the times that I checked my temp, it was in the 130s or 140s, riding around or stopped at the beach. It stayed stable enough that I stopped feeling the need to watch the gauge and just enjoyed the ride. I decided to head toward home a little after 4:30 in the afternoon. I usually turn off of the main road through the beach at an intersection that can get pretty busy. I stopped in the turn lane at 4:35 and my temperature was already at 172 degrees. From looking back at the video, it appears that it had started slowly heating up not long before this. That was the hottest point of the afternoon, and the asphalt and everything else was pretty well heat soaked, but it wasn't that much hotter than the rest of the day had been. By the time traffic started moving, it still wasn't over 180, so I thought I'd be fine. Then the light turned red before I could get to it, and the temperature had shot up to 193 when I looked down. When traffic started moving for the next green light, it was at 217 degrees. probably should have continued and cut off traffic to get moving, but I stopped and waited with coolant temperature rapidly rising. By the time I left the light and got moving, the gauge said 235 after a total of about 4.5 minutes to get through. Okay, well, now I'm moving, so it should cool down. Or maybe not. It was only getting worse, so I pulled into a car wash and shut it down at 249 degrees. If I had my way, I'd never see it past 180. So this was way too hot, and I wanted to get it cooled off quickly. So I sprayed water through the radiators and used the air dryer with the engine running intermittently to circulate coolant until I got the temp down to the 120s. I hopped back on, and in under a mile it was back up to the 230s. I pulled into a gas station, topped off the fuel, and parked to let it cool down. In the meantime, I bought a liter of water because I thought maybe it lost some coolant when it overheated the first time. Sorry I didn't film when this was happening. It was a long hot day that was starting to fall apart, and I didn't even think about video right at that time. After the temperature dropped, I removed the radiator cap and coolant was up to the top. Alright, well, maybe an air pocket ended up in the system. I used an 8mm wrench from my toolkit to open the bleeder valve and steam hissed out before turning into liquid coolant, so there was certainly air in the system. I topped off with water and hit the road again. Within half a mile, coolant temp was back to the 240s. I pulled into a parking lot and once again let it cool, but the temperature wasn't dropping much. I thought perhaps I needed to be more thorough with the bleeding, so I used the bleeder valve to get more air out. Then I took off the radiator cap and refilled the radiators before starting the engine and letting it run while keeping it topped off with water. It took about half a liter of water in a system that only used just over 1 liter total, and then the temperature started dropping quickly. Nice. I must have finally got the air bubble out of there. It started running fine again after that. A little warmer than normal, but not much, and I hope that was just because of the hot afternoon. 11 or 12 miles later, the temperature was in the 160s and climbing as I went through a shaded swamp area where it was a little cooler. Leaving the swamp, it was about 180 degrees and started rising quickly again. I pulled over at the first spot with a shoulder and some shade to go through the whole process again. I did get you a quick clip of some air coming out of the bleeder valve on one of my last attempts this time. By this point, I was concerned that I could have a head gasket leak pressurizing the cooling system, but I never noticed bubbles in the radiator or steam from the exhaust. Regardless, I wanted to make it home, so I got back to riding. The engine ran pretty much like it did the last time, a bit warmer, but otherwise no obvious issues. It ran that way for about 10 miles, and then the gauge started shooting up again, so I pulled into a place called Lucky's Garage, where I at least had some nice scenery while I let it cool before bleeding and topping it off again. I was sure more was going on than air bubbles, but I was a little under 40 miles from home, so I thought at least making it 10 miles at a time I could get home eventually. It didn't last 10 miles that time though. A few miles later I was back at a gas station doing it all over and using the last of my water. I pulled out of there and it immediately heated up, so I went to a drugstore and bought 2 liters of water as a last-ditch effort to keep making progress toward home. I sat out in the parking lot and tried to get all of the air out of it, but it took a whole liter of water and I started seeing bubbles in the radiator, which is a good sign of a head gasket leak. It was also starting to cut out a lot while idling. I figured I had nothing to lose at that point, so I topped it off and gave it one last shot, which I expected to be a failure. Sure enough, it heated up very quickly, and I only made it to a different parking lot in the same complex before shutting it down. It was almost 9 p.m. by then, so I had spent over 4 hours making it 35 miles. With it now going a quarter mile at a time, I gave in and called to get a ride home in the truck. I tore the engine down later and found that it was indeed a head gasket failure. The O-ring melted all the way through in one spot and partially through nearby. Otherwise, everything looked good. I noticed that I didn't see a lot of scuffing that I typically see with air-cooled cylinders. I had another gasket set on hand, so repair was mostly a matter of cleanup and reassembly. Initially, I thought the head gasket failed at the red light or after when temps were high, but after seeing that the temperature was higher than it had been all day even before I stopped at the light, it may have began to fail before any overheating and just continued to degrade. Whatever the case may be, I knew I wanted to take measures to avoid any overheating in the future if possible. My first thought was a cooling fan. Most moto and auto cooling systems incorporate a fan for the radiator because radiators aren't nearly as effective without much air moving when the vehicle is stopped. Fans can be set up as pushers that push air through from the front of the radiator or pullers that pull air through from behind the radiator. Pullers usually work a little better than pushers. At first I checked out PC fans after hearing from others that have used them rain or shine. Lots of computer fans can move quite a bit of air and are sized appropriately to fit a variety of radiators that a scooter would use. Then I found a 4-inch puller fan made by Spall that was intended to be used with radiators or coolers exposed to the elements, so I thought it may be a better choice. It's rated to move 147 CFM and draws about 1.5 amps continuously and 4 amps briefly as it spins up. 1.5 amps is a big deal for a small scooter's charging system, but based on what I saw, I didn't worry about it because I would expect the fan to hardly ever be on. For maximum effectiveness, the fan should be mounted where the coolant is the hottest in the radiators, so it can take advantage of the greatest temperature differential. Near the inlet, where coolant comes from the engine, should be the hottest part of a radiator setup. In my case, the hose present near the inlet made it easier to mount the fan near the top of the other radiator instead. I used a set of zip tie-like nylon cable mounts for a quick installation. The ones that I bought had ends too large for the small fan, but you can find them with small ends or just trim them as I did. They use stick-on pads that go between the fan and the radiator that I also had to trim. Once the pads were in place, the cables could go through and the assembly was put in place on the radiator. Then I pushed the cables through the radiator's core. I slid the locks on from the other side and gave each cable a tug to secure them. Trimming the excess cable finished the job of mounting the fan. Then I needed to wire the fan, but there are a couple of common options for electric fan switching. The easiest way is to use a switch or a switch and a relay to manually turn the fan on and off. That gives the rider the most control over the fan, but it also means that the rider must pay attention to the coolant temperature to prevent overheating, since you probably won't be able to leave the fan on full time because of the electrical demands. I chose to go with a little more involved plan that could take rider error out of the equation to make a safer system. I wanted to use a temperature-activated switch that would make the fan turn on whenever the coolant temperature reaches a certain point, and then turn it back off after the temperature drops. Wiring the fan as shown accomplishes a few things. The fan will be automated, just like production vehicles that come with electric fans, so I shouldn't have to think about it. A switch on the ground side of the relay also allows the fan to be turned on manually. That's good in case the temp switch ever fails, or if I want to try to cool the engine before the switch would activate. Being activated only when the ignition switch is on, make sure that the fan can't come on when the scooter is off and drain the battery. I found this temperature switch specified to turn on at 180 Fahrenheit and off at 165 Fahrenheit with 1/4-inch NPT threads for mounting. I needed a way to place it in the radiator hose, so I made an adapter from a piece of aluminum rod on the mini lathe. I don't think they do much at all, but I added the ribs for surface area, so maybe the adapter can take some fraction of a degree of heat away from the coolant. It was drilled and tapped to accept a 3/8-inch NPT fitting. That's because I knew the temperature switch would be large, so it would need to be spaced out to avoid blocking the whole coolant passage. I installed an aluminum 3/8 to 1/4-inch NPT adapter with JB weld on its threads to be certain that it won't come loose. The temperature switch needs to be installed into grounded metal, so I drilled and tapped the hose adapter so a bolt could be installed and allow ground wire connection. Once the JB weld cured, the switch was installed with liquid thread sealant. The switch does protrude into the cooling passage some, but it should not be a restriction because there are other parts of the cooling system with a smaller diameter than this adapter. I installed the adapter and switch on the hot side hose, even though many instruction sheets say to place it on the cool side. Ideally, I'd like 180 to be the highest temperature that I see, and if I installed the switch on the cool side, the hot side would actually be hotter than that, so this way makes sense for me. I ended up with a snug fit against the frame, so I cut a piece of 3/4-inch ID hose and placed it around the adapter to avoid rattling or wearing parts. When I got to test the fan later, it came on at 178 degrees according to my gauge, and quickly reduced the temperature to 170 before shutting off. That's close enough for me, and I was pleased with how well the fan worked. During the post-meltdown process, I also explored the idea of an electric water pump. It was suggested to me that having more flow while at idle may keep the engine cooler. I felt that airflow was the answer, but increasing flow didn't sound like a bad idea either. I did some searching for electric pumps and ordered a heater pump from a Toyota Prius, because it was only supposed to draw about 0.4 amps, and it had worked well for forum member Ryan Ott. As soon as the pump arrived, I checked the current draw, and it was right around where I was told it would be, at about 0.4 amps. Then I wanted to find out how much water the pump could move within a minute so I could have a spec to compare with other pumps. I did 30-second flow tests, transferring water from one bucket to another. Then I measured how much water was transferred and doubled the 30-second amount to get common specs. I repeated the test twice in hope of increasing accuracy, and according to my results, the heater pump moves 11.6 liters per minute. That didn't mean much to me though, because I didn't know what the mechanical pump flowed or how much flow is really needed. My next move was to test the mechanical pump's flow the same way. I let the engine idle at 1500 to 2000 RPM while transferring water for 30 seconds. After 2 tests, it averaged 9.4 liters per minute. It did fall short of the Prius pump by roughly a 20% difference, but the mechanical pump should increase flow as RPM rises. My next check was to run the engine at about 2500 to 3000 RPM and see how much water it moved. This time it averaged 18.6 liters per minute, so at just a little above idle, it transferred over a 45% greater volume of water than the Prius pump. That still left me questioning exactly how much flow is required, so I started trying to gather information about other pumps for comparison. Here's a quick rundown of what I could find for pumps in a range expected to be appropriate for the application. I wasn't able to find information for all pumps, but what I looked into mostly ranged from a half amp to 2 amps draw with flow rates topping out around 20 liters per minute. Adding more info only seemed to complicate the question of how much flow is really needed, and also led to the suggestion that perhaps too much flow could be a bad thing, because coolant needs time to transfer heat away from the engine and out through the radiator. I've heard that many times over the years in automotive-related discussions, but I never knew if it was true or not, so I did some searching and reading to see if I could find an answer. From what I read, it sounds like coolant needing to move more slowly or in lesser volume to improve heat transfer is a myth, but there is a point where moving more coolant will accomplish very little additional cooling and would cost more horsepower or battery power than it's worth. That's good to know, but 190mech of the 49ccScoot.com forum found what may be a better guideline of 1 liter per minute per horsepower based on comments from the engineers at Aprilia. I found some rules of thumb that would require significantly less flow than that, but they were based on large automotive engines and probably aren't relevant to us. Based on the 1 liter per minute per horsepower idea, my mechanical pump should flow enough for nearly 20 horsepower, not far above idle. I don't really know, but I assume my engine is probably around 10 to 15 horsepower, so I decided to stick with a mechanical pump. While I was testing the mechanical pump, I realized that there was an issue that could degrade the cooling system's performance. I'm not exactly sure what I was or was not thinking when I put it all together, but my hoses were routed incorrectly. I was moving hot water into the bottom of the radiator that should be cooler, and using the top that should be warmer to supply water to the cool side. I rerouted the hoses as they should be and hoped that that would keep the engine running cooler. I also added a pulley overflow tank so the cooling system would be less likely to lose coolant or draw in air if it does run hot. To sum it up, the changes that I made after the overheating and head gasket failure were properly routing coolant hoses, adding an overflow tank, and installing an electric fan. My first ride after the changes was another trip to the beach on a hot day. I left before 8 a.m. when the temperature was only in the 70s and rode most of the first 8 miles cruising at 55 to 60 miles per hour with coolant temps staying between 128 to 130 degrees. I went through a town without any stops and it cooled about 10 degrees with a low throttle cruising. Everything seemed to be working pretty well, but I couldn't really tell if there was much improvement from the hose routing because I hadn't rode in cooler temperatures much before with this build. Ambient and coolant temperatures rose a little as I headed toward the beach, but around 25 miles into the ride, the scooter started topping out at 55 miles per hour or less. I thought it must have been more windy than I had realized until I broke a belt within a mile or two. I pushed the scooter down a side road where I could sit off of the road and in a little shade to change the belt. I cleaned the fluff and strands that were once a belt out the best I could, but there was still a strand stuck in the center of the rear pulley that I just couldn't get out. In addition, the rear pulley seemed to be bent or warped because it would rub the case when turned. I could either get a ride home or put it back together in hope of limping it home. I thought the rear pulley may be messed up anyway, so I figured I might as well take my chances trying to ride it home, and I put a spare belt on. It was immediately apparent that the CVT wasn't working as well as it should be. By the time I got to the end of the road, it started bogging like it was stuck in high gear and died when I stopped. I pushed it to a parking lot down the road and took the CVT cover off again. Now the rear pulley was totally locked against the case. I didn't know exactly what the problem was, but I knew I didn't have the tools to fix it, so I got a ride home in the truck again. Once I could check it out, I found that the rear pulley had broken apart at the weld where the shaft meets the drive face. Luckily, I found a great deal on an overrange kit with a newer aluminum pulley and picked it up not long before this happened. The aluminum pulley required some modification and tuning because even with the same torque driver and drive face angles, it didn't work quite like the old steel pulley for me out of the box. Eventually I got it working well enough to try a beach ride again, and I left just before 9 a.m. with temps in the upper 70s. I cruised 50 to 55 miles per hour with coolant temp staying around 130 to 135. The temperature dropped in the next town and was at 125 degrees when I had to stop for a paving project. After 6 minutes of sitting in the shady area, coolant temperature rose to 139 just as traffic started moving from the opposite direction. The gentle breeze of traffic passing was enough to take the coolant down to 135 before I got moving again. Later, I came to a town with a detour, and I wasn't sure how to get around it any other way, so I ended up on a highway briefly. The highest temperature on the way down happened on the highway, and it was 154 degrees while using a lot of throttle to fight wind and maintain speed on the highway. Otherwise, it ran 140 to 150, cruising 50 plus as the outside temperature approached 90 degrees. I got to the beach and rode around for hours, and the temp gauge stayed in the 120s and 130s, whether I was cruising or sitting at a red light. That's about 10 degrees cooler on average than my last trip. As usual, I was on the lookout for other scooters, and I did find a Yamaha Vino. I caught another light with him and tried easing into it at first, but it didn't matter. I tried to play with a few other vehicles throughout the day, but that didn't get very far. After around 3.5 hours of cruising up and down the strip, it was time to head home. I took the same red light that I had trouble at on the last beach ride, and the coolant temp was 130 when I stopped. This time, the light only lasted a minute, and the gauge still showed 130s when I was moving again. I rode 35 miles, mostly cruising 3/4 to wide open throttle at roughly 60 miles per hour when not going through towns, and the temperature stayed between 140 and 150. I decided to ride around a larger town that I normally avoid, partially because the traffic is a little different there and it was the hottest point of the day, so I could cover about any conditions that I'd normally encounter, and partially because I felt like adding a few miles to the trip. I got caught in a minor traffic jam there because of an accident that appeared to be caused by a truck losing debris that struck another car, but the temp never passed 140. I continued toward home and did a little extra riding in a different town another 15 miles away. There I came across a guy on a motorcycle that seemed to be a bit unsure of exactly what I was riding. From there I made my way home, arriving at 6:30 p.m. to total 242 miles and over 9.5 hours for the day. Finally, a successful beach trip with no help from a truck. The fan never even came on once, or got within 20 degrees of coming on. I still don't regret adding it though, because now I know it's there if I ever do need it, and that gives me some peace of mind. Each day that I went to the beach, I noticed that I had the same amount of power on demand at all times. I've taken a lot of long rides on very similar air-cooled setups, and there's always some difference in how they ran when first started and getting warmed up compared to hours into the ride. I didn't notice that since the water-cooled conversion, most likely because the engine is staying cooler and the air-fuel mixture that travels through the cases and cylinder isn't soaking up so much heat. Short term, that's the main difference that I've actually felt. The engine does seem to tolerate more ignition advance, and dyno tuners have shown that crank-driven fans suck more power, but it's not obvious to me that this engine is much stronger than a similar air-cooled build. Unfortunately, I won't be able to comment on longevity for a while. Definitely not with this cylinder kit, because I've already had an unrelated failure. The wrist pin bearing came apart, and pieces of it battered and scarred the piston, cylinder, and head. Back on track, I like the liquid-cooled rig, and I think it's a good thing in many ways. I can't say that it's for everyone though. There's something to be said about the simplicity of an air-cooled engine. My best advice would be to consider exactly what you want from your scooter and weigh out the pros and cons of liquid cooling versus air cooling to decide what's right for you. As always, if you've enjoyed the video or learned something, please give it a like and subscribe if you haven't already. Thanks for watching.